So in this video, we will discuss about operational amplifiers. So the video is going to have the following structure. First, we will introduce what an operational amplifier is, or first, there'll be an introduction. Secondly, we will discuss how these operational amplifiers, how they work. And thirdly, we will discuss the ideal versus non-ideal behavior of operational amplifiers, which is very important when we are doing circuit analysis. So what is an operational amplifier, right? This image here shows the symbol of an operational amplifier. An operational amplifier has two input terminals. In this case, V1 and V2. The input terminal with a negative sign is known as the inverting input terminal. And the input terminal with a positive sign is known as the non-inverting input terminal. So we give or we provide input to this device through the inverting and non-inverting input terminals, and then the op-amp would do some sort of calculations, or it will do some sort of operation, and then the output voltage would be provided through the output terminal, right? So very simply, these devices would amplify the difference between the input terminals and provide an output. Now, what happens inside an op-amp? So what happens inside an op-amp is a bit complicated, but it works in 3 stages. So the first stage is known as the differential amplifier input stage, and the second stage is known as the level shifting intermediate stage, and the third stage, or the final stage, is known as the emitter follower output stage. So we give an input signal to the op-amp here through this, and then the voltage or the input that we give undergoes 3 stages. The first stage is differential amplifier input stage, second stage being the level shifting intermediate stage, third stage being the emitter follower output stage, and then we will get our output from this terminal, right? So depending on how this operational amplifier is connected with resistors and capacitors, we can make it perform various mathematical operations. Okay? So how the operational amplifier works. We provide the input signals into the inverting input and the non-inverting input. So into the inverting input, we provide the voltage V2, and to the non-inverting input, we provide the voltage V1. So how the op-amp works is, it takes the difference between these two input signals, right? So the difference would be V1 minus V2, and then it multiplies that difference by the gain factor A. So that difference would be multiplied by the gain factor A. So your output would be the gain factor A multiplied by the difference of the two voltages. And if V1 If V1 is greater than V2, then the output goes positive. But if V2 is greater than V1, then the output goes negative. So as I discussed in the previous slide, uh, the op-amp is a high-gain electronic device that amplifies the difference between the input voltages. This was highlighted by the equation V out is equal to A times the voltage difference V1 minus V2, where A is your gain factor and V1 minus V2 is the voltage difference between the input terminals, right? So as you can see in this image, we can modify the op-amp configuration, or we can configure the op-amp in a particular way such that it could perform various operations, right? And in this case, configuring the op-amp like this makes the circuit behave like a filter, right? And as you can see on the second diagram, having a network of resistors like this makes the op-amp behave as a summing amplifier, right? So here, the op-amp will add the multiple input voltages that are supplied in as an input, and as the output, it will provide the sum of all the input voltages, right? So something that you should note here is we feed the input voltage into the inverting terminal in this case. RF is going to be your feedback, and we obtain the output here. So the output is going to be the sum of all the input voltages. Now we're going to discuss about the ideal versus the non-ideal behavior of operational amplifiers. So under ideal behavior, our first point is that operational amplifiers have infinite input impedance. So as you can see, these are the two input terminals, and the operational amplifier has an infinite input impedance. So as a result, the current entering into the operational amplifier is zero, right? The current entering into the operational amplifier is zero because it has an infinite input impedance. So as a result, the current I1 is equal to I2, which is equal to zero, right? And then we have the second point, which says that operational amplifiers have an infinite open loop gain. So in the previous sections, we wrote V out as the gain factor A times V1 minus V2. So if we were to rearrange this equation, we would have V out for the gain factor A, right? So infinite open loop gain, which is A. So as this quantity A approaches infinity, what would happen to the right hand side of the equation? The right hand side of the equation becomes zero because V out is divided by an extremely large value. V out is divided by infinity, which causes the right hand side to be equal to zero, right? So as the right hand side is as the right hand side approaches zero, we can say V1 minus V2 is equal to zero. As a result, V1 is equal to V2, right? So this property of the operational amplifier, where the non-inverting input is equal to the inverting input, this is known as a virtual short. We say that it is virtually shorted, right? So the second property is due to the infinite open loop gain, the voltage at the non-inverting input is equal to the voltage at the inverting input, right? And operational amplifiers have zero output impedance. Operational amplifiers have zero output impedance. So as a result, the operational amplifier can drive any load without a voltage drop at the output, right? The operational amplifier can drive any load without a voltage drop at the output. And um, also, you can assume that ideal operational amplifiers act like a perfect voltage source. Even that assumption is valid under the ideal behavior, right? But practically, so ideal behavior is theoretical, This is a behavior you would expect theoretically. Non-ideal behavior is a behavior you expect practically in the lab or when you do it in practical, right? So ideally, it has an infinite input impedance. As a result, I1 is equal to I2 is equal to 0. But on the other hand, the non-ideal behavior or the actual behavior of an operational amplifier, it has a very high input impedance, but it's not infinite. It's a finite value, right? So this value can range from 10 to the power 6 to 10 to the power 12 ohms. Okay, and you see how here we assume that the current entering into the operational amplifier is zero, but actually there is a small current that enters into the operational amplifier. This is known as an input bias current, right? So an input bias current is a tiny DC current that is flowing into the input terminals. It is very tiny. It's a tiny input DC current flowing into the terminals. But in the ideal behavior, we assume that the uh, current entering into the input terminals is zero, right? And then ideal behavior two, infinite open loop gain, therefore V1 is equal to V2. But in practice, this is not the case, right? The value of A has an actual finite value. So it has a finite open loop gain, right? And the third property is we assume that ideally that operational amplifiers have zero output impedance. But realistically, they don't. They have a very low output impedance, but that doesn't mean it's zero, right? And we use this, we using this ideal behavior, using these points, using the ideal behavior of an operational amplifier, we derive what is known as the what are known as the golden rules of operational amplifiers, right? We derive our golden rules. So golden rule number one is the current I1 is equal to I2, which is equal to 0, right? This is as a result of infinite input impedance. Golden rule number two is the voltage at the voltage at the non-inverting input is equal to the voltage at the inverting input, right? So these are the golden rules of operational amplifiers, and these are very important when we do circuit analysis using op amps. Right? So these golden rules are very important when we do circuit analysis using operational amplifiers, right? So are these the only is the for the ideal behavior of an operational amplifier? These are not the only properties, right? The operational amplifier has more properties. So some other properties that it would have are um, property number four, you could say bandwidth, right? The operational amplifier has infinite bandwidth, um, common mode, rejection rate, and then we have another property called the slew rate. So in the ideal behavior of an operational amplifier, we assume that all these things are infinite, right? So the operational amplifier has infinite bandwidth, it has infinite common mode rejection rate, it has infinite slew rate. Okay, these are the other properties. We will dive into these properties in one of the future videos. And that's one very important thing that you should know about operational amplifiers is that all these rules, right, all these properties are applicable only when the operational amplifier is operating at the linear region, right? All these rules apply only when the operational amplifier is operating at the linear region, right? That is when there is negative feedback. That is when there is negative feedback present, right? And the output is not stuck at its positive or negative supply rails.